morning. And how are you today? Sure, you're fine. Good. Now, today we're going to begin a new topic, which is called sets. And we're specifically going to look at set builder notation because we're at the grade 9 level now. Now, before we actually get into set builder notation, let us quickly do some revision so that you would be updated with all the things that we'll be looking for. Now, first of all, I would like somebody to tell me what is a set, the general definition of what a set is. Yes, Miracle?
A set is a group or collection of any elements or...
A set is a collection or group of elements or objects or things. Good. Now, the things that are found in a set are called its elements or members. For example, I have a set of students here, and each one of you is referred to as an element, or I can say a member. Now, if I want to show that Himala is a member of my class, I would write H is an element or member, and let me say I call my class A. Okay? Now, Neon is not here today. Neon is not a member of my class today. So I would write Neon N is not an element or member of A. So here we have this Greek letter, and it means when we're using it in sets, it's an element or member of. When we cross it off, it's not an element or member of. Now in sets, we also use some general sets of numbers, and we name them N, W, Z, Q, and there are two others. Now let's start with N. N represents the set of what kind of numbers? Quincy?
Natural numbers.
The set of natural numbers. And where do the set of natural numbers begin, Keisha? From 1. So we have 1, 2, 3, 4, 5. How far more should I go? To 9. Let's go. 6, 7, 8, 9. And if we keep going, we go on. And as Himala said, we would go on to infinity. So what we're going to do, we're going to put 3 dots here, and then we're going to close using our opening brace and our closing brace or a pair of curly brackets. Now, because this set would go on and on and on, we call that set an infinite set. And this is what indicates to us that it's infinite. So we move from N, set of natural numbers, we begin at 1, and then we move on to W. W represents the set of numbers. What type of numbers? Himala? Whole numbers. And Miracle, where do whole numbers begin? From 0. So we have 0, 1, 2, 3. Should we go all the way to 9? No, let's cut it off. 4, and so on. So here again, we have another set of infinite. Here we have another infinite set. So we move from natural to whole, then we move to Z. And Z represents the set of, Quincy?
Integers.
Integers. And integers, here we have all positives and all positives. Who can tell me what is different about integers?
They have both negatives and positive numbers.
They have both negative and positive whole numbers. So we're going to start from the negatives, -3, -2, -1, 0, 1, 2, 3, and so on. So if we look, we can see all the natural numbers are in our integers, and all our natural are in our whole. All our whole are in our integers. From integers, we move on to Q, and we call Q the set of rational numbers. And all numbers that we can write, that when we do a division, the numbers terminate or recur, we call them rational numbers. For example, 2, 5, a quarter, 5/10, and so on are all rational numbers. When we take the set of rational numbers and we put them together with another set of numbers called irrational numbers, we make up a larger group called real numbers. Now, as I was saying, that rational numbers can be written in this form. Fractional, a numerator divided by a denominator, but the denominator must not be equal to 0. An irrational, on the other hand, cannot be written in this form. Second characteristic, rational numbers terminate or they recur. Now, what do we mean by terminate? If we find the square root of 16, the answer is either a positive 4 or a negative 4. Finish. Comes to an end. What do we mean by recur? When 5 divided by 11, what do we have? 0.45454545. So what recurs? 4 and the 5. So what I have here is a dot over the 4 and the 5 indicating that those two numbers recur. Here we have another terminating one. When 3 is divided by 8, what do we have? 0.375. The division comes to an end. However, if we look at an irrational number, like the square root of 7, we find that our answer is 2.64575,131. And if our calculator could have accommodated more digits, it would have gone on and on and on and on and on. So it doesn't terminate or it doesn't recur. We don't see any pattern there. The square root of 2/9, 0.47140045. And the same thing, it goes on. And you're there, you're sitting, you do the division, and tomorrow morning is here, you're still going. Okay? Good. So rational, it can be written in this form. It terminates or recurs. Irrational cannot be written as a fraction. And it does not terminate or recur. And when we put the two together, we form the set of real numbers. Now, remember, we're looking at set builder notation. So we'll be using all of these different numbers and symbols to show or demonstrate what set builder notation is all about. We also need to use inequality signs in set builder notation. So let's revise them. So we have 1, 2, 3, 4. I can't give them a name as yet. We have to place symbols before and after, and then we read. So if I write here X, and I put it like that, and I put 2 at the back, this reads X is lesser than 2. Now let's change it up a little. I'm going to put my same X again, but I'm going to turn the sign around. What does this read, Miracle?
X is more than 2.
X is more than or X is greater than 2. Now what about this? I have 2 there. Does this one and this one read the same thing? This one reads X is lesser than 2. Quincy, what does this one read?
2 is greater than x.
2 is greater than x. So if I say x is lesser than 2, and then somebody else says 2 is greater than x, are the two persons saying the same thing? Yes. So how you read it is where the symbols appear. Okay? So not because we take this here and we swing it around and we get this means it's telling you something different. It's the same thing. Good. Now let us see how we can apply all these symbols and numbers that we learned about to set builder notation. Now in sets, you're accustomed to listing sets. We have our elements, we have our pair of braces, we have the name of the set. So we have the set A is equal to 1, 2, 3, 4. Or if we don't want a list, we can describe using words. The set of natural numbers lesser than 5. Now we don't want a list like this, or we don't want to describe. We want to put this same set in set builder notation form. Before we go there again, we need to learn about some other symbols. The pair of brackets means the set of. The colon reads such that. The comma reads and this Greek letter reads belongs to. Now let us take this same set here and try putting it in set builder notation form. So we have the set A is equal to 1, 2, 3, 4. How many elements are in that set? 4 elements are in there. Good. If I ask you for a natural number lesser than 5, which one will you choose? Anyone. We don't know which one to choose. So what we're going to do is to take a variable x to represent. It can be 1, it can be 2, it can be 3 or 4. I don't know which one as yet, but I know it has to be one of these. Okay? Good. Where are we taking these numbers from? We're taking them from the set of natural numbers. So we have to say that. Now when we look again, we know that x has to be lesser than 5. Or x is lesser than or equal to 4. So we know x is lesser than 5. And if x is a natural number, and it's lesser than 5, it cannot start at 4. And it ends at 1. Or we can have x is lesser than and equal to 4. So if x is a natural number and it's lesser than and equal to 4, then it has to be 4, 3, 2, 1, and 1. Good. Now let's put this here in set builder notation form. So we have the set A is equal to, we open our brace, it's a set of x's such that x is lesser than 5 and x belongs to the set of natural numbers. And we close. Let us go again. The set A is equal to the set of x such that x is lesser than 5. Where are we taking x from? X is an element or member, or x belongs to the set of natural numbers. So if x is lesser than 5 and x is coming from the set of natural numbers, x can only be 4, 3, 2, or 1. Now let's see how we can fit this one in. The set A is equal to, we open, the set of x such that x is lesser than and equal to 4. x, and x belongs to which set of numbers? Natural numbers, so we use n. So the name of the set is A, and A is equal to the set of x such that x is lesser than and equal to 4, and x belongs to the set of natural numbers. So you know where to go to find x. And it gives you a range for x. X can't be more than 4, and it cannot be less than 1. Because the minute you go below 1, you're getting out of the boundary of natural numbers. Good. Now, in the second example, I have the set of whole numbers greater than 5. In the first example, we were looking at lesser than. And if you notice, the x was at the beak, the closed end of the sign. See, it's closed, at the closed end. Here we have greater than. Now, what you're going to do for me, go ahead and try writing this worded set in set builder notation form. Good. Now, when we look at this statement here, which set of numbers are we taking x from? Whole numbers. And that is represented by the letter W. So let's put that down. W. Now, if x is going to be greater than, would x be at the closed end or the open end? The open end. So I would write x, and I would write the symbol like that. So x is greater than. Okay? Good. 5. We put in our 5. So here we have x is greater than 5. So it tells me that the whole number begins from where?
6.
6. It begins from 6. So this one tells me that it's greater than 5, and it has to begin from 6. So if we have, according to this, to the signs here, we have 1, 2, 3, 4. We have already used this one here. Of the other 3, which is the next one we can use? The second, the third, or the fourth? The third. Very good. The third one. So we can also use x is greater than and equal to 6. So that tells me I can have 2 displays. The first one. What can we name this set? Miracle? B. The set B is equal to, we open our brace, x such that x is greater than 5, comma, which says and x belongs to the set of whole numbers. We close. So that's the first one here. Good. So we utilize the first inequality statement, x is greater than 5. Now let us try the second one, x is greater than and equal to 6. So let's fit that into our set. The set B is equal to x such that x is greater than and equal to 6, and x belongs to the set of whole numbers. Now when we look at the sets we're given, the set of whole numbers greater than 5. Now when we look at this one over here, we have the set of natural numbers lesser than 5. Now let's look at the third one. The set of whole numbers between 8 and 4. So we have 2. We have we're contained now between 8 and 14. So if it's between 8 and 14, would 8 and 14 be in them? No. So if 8 is not going to be there, what can we write as an inequality statement showing 8?
X is greater than 8.
X is greater than 8. So we know for sure 8 is not there. What can we write for 14?
X is less than 14.
X is lesser than 14. Now when we get to our set, Himala, what can we name this set?
Set C.
Set C. When we're going to write our set, we cannot put these 2 individually. We have to put them into one and show that X is greater than 8 and X is lesser than 14. So let us see how we can put that together. So let's come down to the bottom here. X is greater than 8. It's greater than 8. X is greater than 8. And X is also lesser than 14. So let's close off the second piece and read. X is greater than 8. X is lesser than 14. So let's finish off our set. X such that X is greater than 8. X is lesser than 14. And where did we get X from? X belongs to the set of whole numbers. Now we use the 2 without the extra piece. Let us try saying the same thing using the other pair. So if X is between 8 and 14, X will be from where to where?
From 9 to 13.
It will be from 9 to 13. So in that case, X would be greater than and equal to 9, and X would be lesser than and equal to 13. So I want you to use these 2, combine it in one, and then write a second C. Quickly. So we start off, C is equal to the set of X's such that, so let us center our X. America, what did you have preceding the X?
X is greater than and equal to.
Greater than and equal to 9. And after the X we would have
Less than and equal to.
less than and equal to 13. And X belongs to the set of whole numbers. So we have used the pairs. Greater than, lesser than. Greater than and equal to, lesser than and equal to. Now let us interchange. Let us try using greater than and lesser than and equal to. Good? So we want, if X is from 9 to 13, then X can also be between or from 9 and it ends at 14. Okay? So if we should rewrite that, we can say the set of whole numbers 9, 10, 11, 12, 13 But we can also say, so we have 2. X is greater than 8 and X is lesser than and equal to 13. So if it's greater than 8 and it's coming from whole numbers, it's got to start at 9. And if it's lesser than and equal to 13, then it stops at 13. So we have 1, 2. Our third C will be X such that X is greater than 8, lesser than and equal to 13. X is an element or a member, or it belongs to the set W. So we have 1, 2, 3 ways in writing the same thing. Now there is a 4th way. Now if you look carefully, you'd see here we have the same pair, same pair. Here we have the first here, and we have this one here. So that means that these 2 can also make 1. So you are going to use this sign and this sign to come up with our 4th example. We're sure we have to have our X here, such that, and our X here in the middle. We're also certain that we're going to have our and X is an element or member of W. So that's standard coming through. So here we have an 8 and an 8 and 9. Therefore, we're going to have a 9 here. What are we going to have here? Greater than and equal to. So we have 2 and equal to here, so we have to get this one here now. And it's lesser than 14. So we have 1, 2, 3, 4 different ways using the pairs of the different inequality signs to show us how to show sets using set builder notation. And remember, the pair of curly bracket means the set of x's. The colon means such that x is greater than 8, lesser than 14, and x belongs to the set of whole numbers. And here we have the name of the set. Now there's one other way in which we can use set builder notation. In this example here, we're given set builder notation to list the elements. Now we have the set P, which is equal to the set of x's, such that x is greater than -6, lesser than and equal to 7, and x belongs to the set of integers. The instruction says list all of the elements of the set P. Now looking at what we have here, will -6 be in the set P? No. So we write our name, P is equal to, and we open. So there's no -6. So what's going to be the first element? -5. Would 7 be in my set P? Yes, because we have this little thing at the bottom there, that little stroke. So it's -5. What's the next one? -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, and 7. And we close. So by now you're seeing the pattern. If this inequality sign doesn't have the stroke, it means that it's not included. If the stroke is there, you include the element. Good? So that's example 4. Example 5, we have the set M, the set of x's, such that x is greater than 2, x is lesser than 8, x belongs to the set of natural numbers. Go ahead and list all of the elements of the set M for me quickly. Himala, would 2 and 8 be in the set M? No. What's the first element, Himala? 3. Followed by?
4,
Uh-huh.
5,
5, 6,
7.
and 7. And we close. So we can either take a set and write it in set builder notation form, or take the set builder notation form and show it by listing it. Now let's look at the final approach to set builder notation for our lesson. We want to demonstrate ordered pairs. And our ordered pairs in sets and mass would be a pair in the XY form. Here we have a pair, a X value and a Y value. Now we're given U, a universal set, and the elements are 0 to 5. Now we want to find all the sets that we can have. They must be in XY form, and it must be in such a way that Y is equal to X plus 1. X belongs to the universal set. Y belongs to the universal set. Now what we're going to have is all the elements that we're seeing here, they're all X's. So we have X equals 0, X equals 1, X equals 2, X equals 3, X equals 4, and X equals 5. The X always comes first. We're given those. How do we determine our Y? According to this set here, Y is equal to X plus 1. Y is equal to X plus 1. Now when we look across here, we see X is equal to 0. So we're going to substitute. Y is equal to 0 plus 1. Y is equal to 1. So our first ordered pair, when X is equal to 0, Y is equal to 1. So if X is equal to 1, then Y would be equal to 2. And when X is equal to 2, Y would be 3. And when we have a pair for 0, 1, 2, 3, 4, and 5, we complete our set. The set B such that B is equal to the first pair, the second pair is 1, 2, the third pair is 2, 3, then we have a fourth and a fifth pair, and we close off. You're going to find the fourth and the fifth pair for me and close off there. Good. So what is our fourth ordered pair?
3, 4.
3,
4.
4. So I can put here 3, 4. And I guess you have a fifth one?
Yes,
And what's the fifth one?
4, 5.
4, 5. So I'm going to come here now, and I have 4, 5. I close off. And will we have another one? No, we can't. Because if we use X equal 5, Y would be equal to 6. And what does it say up here? Just look up here. It says y belongs to u. And let's look at u now. U begins at 0 and it ends at 5. So 6 does not belong here. So the ordered pairs that we can have, 1, 2, 3, 4, 5. End. Close off there. We cannot go against this condition. If y does not belong there, we cannot put it in. Okay? Good. Now, today we set out to find out what set builder notation is all about. Now, before we actually got down into using set builder notation, or how it should be written and what it looks like, we had to know about the different set of symbols. We looked at a pair of braces. We looked at the colon, the comma, and some special sets of numbers, natural numbers, whole numbers, integers, irrational numbers. And when we put rational and irrational together, we get the set of real numbers. Good? Now, if we should go back, we're accustomed to seeing sets described or they're listed. In set builder notation, we don't use words. We strictly go for symbols. And we make use of the inequality signs. And we need to be very careful how we read them. For example, here we have the set of whole numbers greater than 5. So we know we're taking x from the set of whole numbers, and they have to be 5 and more. So we write an inequality statement first so we can understand where we're going. X is greater than 5. So we know definitely x will begin from 6. So that's why we can write that x is greater than and equal to 6. So when we go to represent our set B, using set builder notation, we write the set B is equal to the set of x's such that x is greater than 5. X belongs to the set of whole numbers. Or the set B is equal to the set of x's such that x is greater than and equal to 6. X belongs to the set of whole numbers. And remember, we have to close. Okay? Good. Now, I hope that today, in your garden of your mind, you have planted the words of set builder notation, or all the ideas of set builder notation. And I know that that idea will blossom and grow. Okay? Now, that was from me to you. Now let me hear how you found this concept this morning. Anybody? What do you think about set builder notation? Did you enjoy it? What part was your favorite?
It was interesting, and my favorite part was learning the differences between rational and irrational numbers.
What about you, Himala?
Well, I've learned some basic stuff that I didn't know before, and my favorite part was irrational and rational, and the difference between them.
Okay. What about you, Miracle?
Set builder notation was an interesting topic, and I enjoyed learning about the use of the inequality signs.
Okay. Well, let us recap quickly. Look here. Lesson 10. Sets, set builder notation. In this lesson, we will use set builder notation to describe a set whose elements are given. History of sets. Set theory was the creation of one person, George Cantor. He was born on the 3rd of March, 1845 in St. Petersburg, Russia. History of set continues. After Cantor's family migrated to Germany, he became president of the Mathematics Society during the years 1864-1865. The extraordinary professor retired in 1913 and spent his final years ill with little food because of the war conditions in Germany. He died of a heart attack on the 6th of January 1918 in Germany. Here are some key points. The general name for a collection of objects is a set. The elements or members making up the set are enclosed in curly brackets or braces. The symbol means is an element of, or is a member of, or belongs to. What means? In mathematics, we classify numbers that have common characteristics. N, counting or natural numbers. 1, 2, 3, 4, and so on. W, whole numbers. 0, 1, 2, 3, 4, and so on. Z, integers. -3, -2, -1, 0, 1, 2, 3, and so on. Q, rational numbers. What are rational numbers? Let us compare and contrast rational and irrational numbers. Real numbers. Rational numbers can be expressed in the form a divided by b. b is not equal to 0. Irrational numbers cannot be expressed in the form a divided by b. b is not equal to 0. Let us compare and contrast rational and irrational numbers. Real numbers. Rational numbers terminating or repeating decimals. The square root of 9 is equal to positive or negative 3. 2/3 is equal to 0.666. 9 divided by 11 is equal to 0.8181. Irrational numbers not terminating or repeating decimals. Square root of 2 is equal to 1.41422135, and so on. Square root of 5 is equal to 2.23607, and so on. It is important to remember 2 is lesser than 5. It's the same as 5 is greater than 2. Y is lesser than or equal to 4 reads y is lesser than or equal to 4. Reads y is greater than or equal to 6. Set builder notation. 1, 2, 3, 4 can be written as open bracket x such that x is a natural number less than 5 close bracket. This reads the set of all x such that x is a natural number less than 5. Or this reads the set of all x such that x is greater than or equal to 1, lesser than 5, and x belongs to the set of all natural numbers. Given that, we should note that 1. The braces read the set of. 2. The colon reads the set. 2. The colon reads such that. 3. The comma reads and. 4. The Greek letter reads belongs to. Example 1. Rewrite using set builder notation. A. The set of natural numbers less than 6. B. The set of integers greater than -1 but less than or equal to 2. Solution A. B. Example 2. Given A equals, list all the members of set A. Solution. X is greater than or equal to 1. Then x is equal to 1, 2, 3, 4, 5, 6, and so on. X is lesser than or equal to 4. Then x is equal to 4, 3, 2, 1, 0, and so on. X is greater than or equal to 1, lesser than or equal to 4. Then x is equal to 1, 2, 3, 4. A equals 1, 2, 3, 4. Example 3. Given B equals, list all the members of set B. Solution. X is greater than -3. then x is equal to -2, -1, 0, 1, 2, and so on. X is less than or equal to 3, then x is equal to 3, 2, 1, 0, and so on. X is greater than -3, less than or equal to 3, then x is equal to -2, -1, 0, 1, 2, 3. The set B is equal to -2, -1, 0, 1, 2, 3. Set builder notation can also be used to describe sets whose elements are ordered pairs. Example 4. Universal set U is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8. List all the subsets given by G equals solution. When x is equal to 0, y equals 0. When x is equal to 1, y is equal to 2. When x is equal to 2, y is equal to 3. When x is equal to 2, y is equal to 4. When x is equal to 3, y is equal to 6. When x is equal to 4, y is equal to 8. G equals 0, 0, 1, 2, 2, 4, 3, 6, 4, 8. Y is equal to 2 by 3, which is equal to 6. Summary. Rational and irrational numbers are subsets of real numbers. Set builder notation is a method of defining the elements of a set. Example, the set of x such that x is greater than or equal to 1, less than or equal to 4, x is an element or member of the set of integers. Set builder notation can also be used to describe sets whose elements are ordered pairs. Example, G is equal to the set of xy's such that y is equal to 2x. X is an element or member of the universal set. Y is an element or member of the universal set. Problems for today. Page 26, exercise 3A. Questions 4, 8, 12, 16, 20, 24, 28, 32, 36, 40, 44. Mathematics for Secondary Schools in Guyana, Book 3. Solution for the problems given in the last lesson. Page 22, exercise 2O. Use the iterative method to find the square root of 42. Number 6, solution. The square root of 42 lies between the square root of 36 and the square root of 49. That is between 6 and 7. Since 42 is between 36 and 49, we can estimate square root of 42 as 6.5. By the iterative method, the square root of 42 will then be equal to half into 6.5 plus 42 divided by 6.5. The square root of 42 is equal to half into 6.5 plus 6.46. The square root of 42 is equal to half of 12.96 equals 6.48. Solutions for problems given in the last lesson continues. Page 22, exercise 2O. 10. Use the iterative method to find the square root of 79. Solution. Square root of 79 lies between square root of 64 and the square root of 81. That is between 8 and 9. Since 79 is closer to 81 than 64, we estimate the square root of 79 as 8.9. By the iterative method, the square root of 79 will then be equal to half into 8.9 plus 79 divided by 8.9. Square root of 79 is equal to half into 8.9 plus 8.88. The square root of 79 is half of 17.78 equal to 8.89. Good. So let us quickly recap what we did for today. We're showing sets in another way, because as you went through your grade 6 and your grade 7 and your grade 8, you know you came about loops and listing and so on. Now this is another form, okay? And I hope you had a lot of fun. And as I said, you're going to go and you're going to make full use of all that we did today. And if you know there's somebody who doesn't know it, make sure you teach them. Okay? Enjoy the rest of your hour.